Let's talk about the effect of temperature on the rate of a reaction in a little more detail than we did before. So Svante Arrhenius was the individual who proposed the idea that for a particular reaction, there was an activation energy necessary for collisions to be effective. And he not only made that statement, he came up with a mathematical expression to explain what was being seen and why. And so the Arrhenius equation is K, and so there's your rate constant, whose units, of course, will depend upon the overall order of the reaction that you're looking at, is equal to A, which is called a frequency factor. We'll look at that in just a little more detail here in just a second. Multiplied by E raised to the minus EA over RT. And here EA again is your activation energy. R is your ideal gas constant, but since we're working with energy units, we want the energy form, so 8.314 joules per mole Kelvin. And T is your Kelvin temperature. Let's talk a little bit more about the frequency factor in this. The frequency factor really takes into account two components of our requirements for collision theory. So collision theory said that you had to have enough energy to overcome the activation barrier, so we see that in EA right here. But it also said we had to have collisions that occurred and that they had to have the proper orientation. And this frequency factor takes into account both the collisions and the rate of collisions that are occurring, so collision frequency, and it also takes into account the molecular orientation, which is called the steric factor. In other words, what fraction or what proportion of the collisions that occur have the appropriate orientation in order to have a reaction occur. So both of those are reflected in that frequency factor term. In terms of putting this equation to use, we can actually get a lot of information then between by looking at how the rate constant changes with respect to time. Because if I take this equation and I rearrange it mathematically, I can get the following form that we can use as a linear equation. To make this equation look more obviously like a linear relationship, I'm going to take the term EA over RT right here, and I'm going to break this into two pieces. Mathematically, this is equivalent. I've simply taken the temperature and made it appear as its own term, because what we have at this point is a Y equals mx plus b way of looking at this equation. And so if I go in and I want to determine how temperature affects my activation energy, if I create a graph that is inverse temperature on the x-axis and natural log of the rate constants at different temperatures on the y-axis, I'll get a straight line, and the slope of that straight line is going to be minus EA over R. The y-intercept, which I guess I need to make my line go back farther, the y-intercept of this graph then is going to be the natural log of that frequency factor. So if we want to determine what the activation energy is for a particular reaction, we need to measure the rate constant at a variety of different temperatures and graph natural log of K versus 1 over T. Let's put this equation to use and see what we can do with it. Here's a problem where I have the decomposition of N2O5, and it's going to break down to form 2 moles of NO2 and a half a mole of oxygen. So data was collected for the rate constant at 3 different temperatures. Notice that these are given in Kelvin. If they're given in degrees Celsius, you'll have to convert to Kelvin. But if I take this information, I need to graph 1 over the temperature versus the natural log of K. So there's the values. When I graph them, what I find is a graph that has a slope of negative 12,447. And so given our equation, the rearranged linear form of the Arrhenius equation, my slope is equal to negative EA over R. So negative 12,447 is my activation energy divided by R. And so I can very readily solve for that activation energy just from that simple graph. So if you collect a bunch of data for temperature versus the rate constant, or changing the temperature and measuring the rate constant, you can find your activation energy. Sometimes though, we don't necessarily need to have 3, 5, 7 data points. 2 data points will suffice. And so let's take a look at how we can use the Arrhenius equation and manipulate it in order to use just 2 data points for temperature information. If we take the Arrhenius equation that we've been working with, and we only want to use 2 temperatures, we can do some mathematical manipulations that I'm not going to go into detail on here. I'll be happy to show you if you want. And we'll get the equation in the following form, where the natural log of the ratio between K2 and K1 is equal to EA over R multiplied by the difference in those inverse temperatures. The only thing that's going to be tricky and that you need to make a point with when you're using this equation is to keep track of which is temperature 1 and which is temperature 2 so that you're consistent with your rate constants and your values for those temperatures. Reminder, R is again 8.314 joules per mole Kelvin. And therefore, in order to have all your units matched throughout the equation, you have to be using the Kelvin temperature, or this does not work. Let's take a look at 2 examples where we're going to use this 2-point form of the Arrhenius equation. A first order reaction has a rate constants that are 4.6 times 10 to the negative second per second, and 8.1 times 10 to the negative second per second. And those rate constants are occurring at 0 and 20 degrees Celsius. What's the value of the activation energy? So as I mentioned before, the most important thing is to identify what's T1 and what's T2. So let's make this 0 degrees Celsius be T1. And so its rate constant is 4.6 times 10 to the negative second. And then we'll have 20 degrees Celsius be T2. Just so that we are clear when we go to use our equation, what is what. So let's start with the 2-point form of the Arrhenius equation. Now that we have it, we're going to plug our numbers in, taking care to convert the temperatures from degrees Celsius to Kelvin. Once we have all the numbers plugged in, it's simply a matter of solving for the activation energy in order to find the value that we need. So we can use this equation to solve for the activation energy. Conversely, if you know the activation energy, you can actually compare or predict the rate at 2 different temperatures. So let's look at one problem like that. So if you look in this problem, you know the value for K at 298 Kelvin, and you are trying to find the rate constant at 350 Kelvin given a known activation energy. So once again, we're going to start with our 2-point Arrhenius equation, making sure to be aware of what our units are. We're going to plug our values in for everything that we know, and I'm going to have the unknown temperature, so 300, or the unknown rate constant temperature, the 350 Kelvin, I'm going to have that be K2 so that it's in the numerator and is a little bit easier to solve for. So I'm going to plug those values in. Once I have all the numbers plugged in, then I am going to do the math in order to solve for K2. So when I do all of this math, I find that K is 0.702, and since this is a first order reaction, I know that my units are going to be inverse seconds, and since you know that the rate constant at the first temperature had units of inverse seconds, you also know that this rate constant will have units of inverse seconds. All done.